Alright guys, let's take a look at today's lesson. What we're going to be doing is working on Taylor series. This is for day 3. Let's kind of recall what we've done so far. On the first day we learned how to create Taylor series, and if you'll recall, Taylor theorem is quite similar to the Taylor polynomials. We start generating it like a polynomial and then we just come up with an nth term. What I guess would be the difference with this, our general term, versus our polynomials, our Taylor polynomials. And then we also learned how we could substitute into a previously known series. We did that. We learned how to take the derivative or integral of a series and a limit. So we've done a lot of things with Taylor series so far. We're actually going to add another layer today. What we're going to be looking at, we're still going to be generating Taylor series, and Taylor series is a power series. Some students were getting confused with that vocabulary word. Taylor series is like a subset of power series. It's still a power series, as Maclaurin is a subset of Taylor series. Right? Maclaurin is a specific kind of Taylor series where it's centered at 0. So what we're going to do today is we're going to learn how that some of these can be written as a geometric series, and that provides actually some pretty good stuff for us. We know a lot about geometric series. We know how to find the interval of convergence, absolute value r less than 1. We just have a lot of things going for us with geometric series. And a really great thing, and I know some of you are going to be upset about this, but a really great thing, when we find the interval of convergence of a geometric series, we don't have to check the endpoints. Oh, I know. That's such a bummer. Because as a result of the way the geometric series is created, the endpoints are never included. Okay? Never. Darn. Now, if you want to go ahead and check the endpoints just for fun, you certainly can, but the endpoints are never included on a geometric series. So there's a lot of benefits to being able to write one this way. So before we start in, let's kind of remind ourselves about geometric series. Let's look at a couple of formulas. One that we used in pre-cal quite frequently, which was actually causing some of us to have some issues. A sub n equals a times r to the n minus 1. This was very common with pre-cal, and this is when n started at 1. The one we use in calculus a little bit more frequently is a times r to the n, and this is starting with the n of 0. So that was causing us a little bit of trouble earlier in determining what a was. Depends on where you start. So these are just a reminder from a couple of different formulas. If we wanted to write a geometric series starting with a of 1, if we just wanted to write it out, remember r is our ratio and it's basically our multiplier. We just multiply by it over and over again. So it would be 2 plus 6 plus 18 plus 54 plus dot 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 plus, and our formula would be 2 times 3 to the n. That would be our general term. Just to kind of remind you, just a regular geometric series where the first term is, see, I'm using this second piece right there. I'm starting at an n of 1. Doesn't mean that you have to, it's just that's what I'm doing. Remember, we talked about that before. You can start at it, whatever, n of 1 or 0, whatever you want. So that would be just a regular geometric series. Well, what if we were asked to write a geometric series with an x in it, like this one, where we start with a 1, and then it's basically x to the first, to the second, to the third. So 1 plus x squared plus x cubed plus, and then our formula would be x to the n. You could put 1 times x to the n. 1 is my a, but I mean it's 1, so you don't have to. If we wanted to write it in a summation, this particular one starts at 0, and that would be my summation if I wanted to write it in a summation. Certainly it says general term. You can just write the general term, which we know is this one. You could certainly write it in sigma notation as well. Alright, so what we're going to do is we're going to, if our function is kind of, here's what we're looking for if you'll recall. For an infinite geometric series, the sum was a over 1 minus r. Remember that formula? If our function is kind of in that form, we can force it into a geometric series pattern. Now, if it's we might have to do some algebra to mess with it, but for the most part, pretty straightforward. This particular one that we're starting with is actually identical. There really isn't. I have my 1. This has to be a 1 right here in the formula, and basically A and R can be whatever, but this has to be a 1. And so I know from this pattern that A is going to be 1 and R is going to be x squared. I know that from the format that this function is written in. If I'm going to force it into a geometric series, these are the steps that I would take. So it wants us to give the first 4 non-zero terms in the general term. All right, so we'd start with the 1, and our next term would be x squared, and our next term would be x to the 4th, and then x to the 6th. So what do we want? 4 terms. And then our general term, really, we just default to this. It shouldn't be really difficult to find the general term. We're just going to use this formula, the A and the R. So 1, so it would be x squared to the n, and I could have a 1 in front of there if I wanted to. I mean, that's my A, but we know 1 isn't required. And you can simplify that. You could do x to the 2n if you wanted to, but that would give me my general term. Our interval of convergence is where absolute value of R is less than 1. And we had some confusion earlier today on how to do this. We've done this before. Not really sure where the confusion comes in. We don't square root both sides. If you'll recall, that's not a thing that we do. Well, so here's the thing is this statement is going to always be true. Right? No matter what I put in for x, it's always going to be bigger than -1. So really, I don't even consider that part, because it's always true. This is the piece that I would have to work. X squared less than 1. And if you'll recall, I have to do a sign chart and test the signs. Some of you already know what this is going to turn into. Basically, my signs would look like this, and I want it to be smaller, so my interval of convergence is between -1 and 1. And I don't have to check the endpoints. I don't have to check the endpoints because this is geometric, and we know that the endpoints are not included in geometric. So this would be from -1 to 1. All right. There are actually 2 other ways to do this. So I'm going to talk about the 2 other ways. Certainly it's your choice how you do it. I kind of tend towards working it geometrically. You could do it the way we did it previously, to generate them, which is writing, doing all the derivatives of it. So we would take the first derivative, and that would be kind of a little painful, right? And then I would do f prime of 0, and I would get that number. We would generate it the old-fashioned way. Are you with me? You would do all the derivatives and just generate, and you would get this exact same thing if it were simplified. Okay, that's one way to do it. But as you can see, this derivative is going to get pretty messy, because not only the first derivative was a power chain, but everyone afterward is going to be a product and a power chain. Because I have to do the product rule and then power chain it, or a quotient rule, something kind of crazy. So working it this way, while doable, would be much more intense than doing the geometric, than working it geometrically. So that was where I would tend. And there's a third way you can do this, which is kind of really crazy off the wall, but I wanted to show it to you because it is kind of crazy off the wall. You can actually generate this power series by dividing. I know, crazy. Let me show you. You can actually divide. Let me move some of this stuff out of the way. So I could do 1 divided by 1 minus x squared. I take my function and divide it. So 1 goes into 1 one time, so I multiply back out. And then subtract, and then I'd get what, x squared. And basically, what times 1 would give me x squared? It would be, x squared, and then I'd multiply back out. Is that not totally cool? And so it's going to generate this series across the top. I know, that's crazy. It's crazy. That's kind of a crazy way. Now, if you do it this way, it's kind of fun and crazy, but you're going to have to find the nth term, right? Or the general term, shall we say. Find the general term, and then you're going to have to do the ratio test to determine if it's convergent or not, and then you're going to have to test the endpoints because it's not geometric. So though it's cool, it's still, I think, a bit more work than the geometric technique. I really like, as you can see, I'm kind of tending towards the geometric technique. It's kind of nice. So if your function is written in this type of fraction form with something, a monomial on top and a binomial on the bottom, there are many times that you can force it into geometric. Okay? They would have to look like this in fraction form. They have to be looking similar to this for that to work. Okay, so just a little aside, just so we can understand conceptually what's going on. On my calculator, I'm going to pull it up in just a second. What I have done is I've put the function, this little guy right here, in y1. And then in y2, what I've done is I've typed in the first 5 terms of the series. Okay, I've typed that in. And what we're going to do is we're going to look at it on the graph. I'm going to talk to you about a couple of things. You can have the calculator out or not. It doesn't matter. This is really the only thing we're going to be using it for. So if you'll note, I have my function in y1, and then I have my first 5 terms in y2. Okay, so let's graph it and take a look at what it looks like. So that's the original function. And then that's my Taylor polynomial. Okay, notice how in the center it matches very well. If you look at our table, you'll notice that comparing these at point 1, point 2, point 3, they are virtually, almost identical. The farther you get away from 0, certainly they're not exactly the same, but they're very, very close. If we go down and look, let's kind of look at the 0.8, we're pretty close. 0.9, we're starting to not be as close. But look at what happens after 1. It's just way off, right? And this is because it's in the interval of convergence, right? And the interval of convergence is between -1 and 1. And so if we look at the behavior of our original function and our Taylor series between -1 and 1, they are very, very similar. But if you get outside that interval, outside of -1 and 1, they behave quite differently, that's what the interval of convergence means. That's where they converge. And so I wanted to talk to you about that. It's basically a conceptual thing that we need to understand. What's the interval convergence for? That's what it's for. You could actually graph your original function and the first 5 terms of your series and kind of look at it numerically and see where you think the interval of convergence is. You have to actually do the test to determine, but you could actually look and compare your original function with your Taylor series to determine, where is the interval of convergence, or at least get an idea by numerically with your calculator. Okay, so that I thought was pretty important for us to talk about. Yes, there we go. Okay. All right, so let's take a look at, we have a couple more problems to do. On the next one, we want to find a power series for 1 over 4 plus x centered at x equals 0. So just so that you know, centering it at x equals 0, doing a Maclaurin is quite nice. We have one that's not, and I'll show you how to do that one. It's a bit more challenging, but when it's centered at 0, we're kind of happy about that. And this one is centered at 0. So I have 1 over 4 plus x. And I need this to look like a over 1 minus r. That's what I need it to look like. And so I can't have a 4 there. It has to be a 1. So I'm going to have to do some, algebra. I have to divide out the 4. So I'm going to divide out the 4 and move it to the top. So it's going to be 1/4 over 1 plus x over 4. Okay, dividing out the 4 from the denominator and moving it to the top. It's almost perfect. I have to have a negative sign there. I mean, some of you can just kind of think through that. I'm going to go ahead and rewrite it with a negative. You certainly don't have to. I mean, if you can just go straight to it rewritten, that's fine. You don't have to show the steps. I'm showing the steps so you can see what I'm doing. So this would be 1/4 over 1 minus a minus x over 4. Okay, so now it is in this proper form right here, where I have an a and I have an r. And so my a is going to be 1/4, and my r is going to be negative x over 4. So they want us to write the first 4 non-zero terms in the general term. So let's go ahead and do that. So my first term is 1/4. And yes, it is possible to have an x in your first term, and that's okay. It's okay if it's an x. I think one of our daily work problems has an x in it, and it was troubling some students. That's okay. You can have an x as part of your a term. So I have 1/4 minus x over 16 plus x squared over 64 minus x cubed over 256 plus dot 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 plus. Writing the general term should be very easy for us. We just use the format that we've learned for geometric series. So I put my a term on the outside, my r on the inside to the n power. Pretty straightforward. Once you find a and r, you just sub it into the formula. Now the formula that I'm using, though, is starting at an n of 0. If you want to get fancy and use a different start you've got to use a different formula. Okay? Yeah, just change the n, adjust it whatever you want it to start at. So now they ask us to find where is it converged. So we know absolute value of r is less than 1, and it's absolute value of r, so the negative is going to go away. So I have x over 4 is less than 1, less than negative 1. So negative 4 is less than x less than 4. Okay, do we have to check for the endpoints? No, we don't. Whew. So this is our interval of convergence, and this is our first 4 terms and our general term. Okay, is that okay? All right, our last one is a bit more challenging. Let's talk about why. This right here. We just love Maclaurin series, right? As I look through here, notice how it's like an x squared, x cubed. If this was centered at 2, what would these have to be? They'd have to be x minus 2's, right? I mean, they have to be. That's the way it's supposed to look. They'd have to be x minus 2's. And so that's just not something that's typically embedded in this function, is an x minus 2 or an x minus 4 or wherever you're centered at. So it's something that we have to algebraically force in there. And so we're going to walk through that. Let's do this one. So the 15 over 2x minus 1, okay, we know there's a couple things going on. I need the constant, I'm going to put the constant in front. Okay, so I have a negative 1 plus. And where the x is, I'm going to actually open up that space where the x is, and I'm going to put in an x minus 2. Okay, so I know there's a 2 in front of the x. We're just going to have to ignore it for right now. I'm going to open up this space and put in an x minus 2. Now we have changed the value of this function, so we have to counter it. We have to fix it. So what I actually did was I actually subtracted 4 from the bottom. The 2x was already there, so that's okay. But I actually subtracted 4, so I need to counter that with adding 4. I mean, it's what I have to do. So that work was just embedding the x minus 2 in there. Now once I have that embedded, I need to, which is great, that's like the first step. Or you don't have to do that first. You can do it several ways. But for me, this was the first step. And now what I have to do is I have to get it to look like this. I need it to have a 1 in front and such. So first, let's combine these constants together, the 4 and the negative 1. And I'm left with 15, and then I have 3 plus 2 times x minus 2. All right, so this 3 needs to be a 1. So I'm going to have to factor a 3 out of the bottom and move it to the top. So I have this. Okay, I factored a 3 out of the denominator and I moved it to the numerator. And my last, I'm so close, I need it to be negative. So just to be clear, I'm going to rewrite it with negative. So this would be 5 over 1 minus 2/3 x minus 2. Okay, so now my a is 5 and my r is negative 2/3 x minus 2. So we need to write the first 4 non-zero terms in the general term. So the first term is 5. And then I'm going to multiply 5 times 2/3 and get 10/3 times x minus 2 plus, and I keep going, just keep using my r by multiplying, 20 over 9 x minus 2 squared, and then 40 over 27 x minus 2 cubed, and that's my first 4, plus dot 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 plus. And now I just use my formula. My a is 5, my r is negative 2/3 x minus 2 to the n. And that's my general term. So we want to do our, let's see, we've got the first 4 non-zero terms in the general term. Now we need to do our convergence. So let me move this up here so we can see a little bit better. Okay, so our interval of convergence is where absolute value of r is less than 1. So the absolute value took care of the negative. I don't have that anymore. So it's 2/3 x minus 2 less than 1. It's between negative 1 and 1. Multiply by 3/2. Then I add 2 to both sides. And we recognize we don't have to check the endpoints, but there's one final check we need to think about. Okay, where is this series centered? At 2. If my interval of convergence is not centered at 2, I have issues. Okay, it has to be centered at 2. If it's not, then there's something that went wrong in my algebra, or something happened. And so it has to be centered at 2. Is this one centered at 2? Yes, it is. So we're fine. I just want to make sure we understand it has to be centered at wherever it's supposed to be centered at. You know you made some kind of algebra or arithmetic mistake. Something like that. Okay? All right.